Hello, everybody out there in digital land. Word problems, my favorite. So let's get at word problems. And this should be a nice, easy way to get into it because you should have done Half-Life last year. If you remember anything from last year. And Half-Life is, exponential growth and all that kind of stuff. And it's a really cool idea. And it goes over into chemistry and science quite a lot too. So good stuff. Anyway, cookies. What better way to start a lesson than a box of cookies, especially Girl Scout cookies? So if it has a half-life of 1 day, and you have 80 cookies in the box, how many after 1 day? Well, hopefully you said 40 in your mind. And then after 2 days, half of that 40 would be 20. And then after 3 days, half of 20 is 10. And when I get to 10 days, I'm like, I don't know, let me find a pattern. And hopefully what you're saying to yourself was, well, I took 40, no, not 40, 80 was the original amount of cookies, and I multiply it by half and a half and a half to get the 10, half of half of half, and that's the number of days. 3 is here, so it's actually 1/2 to the third power. So hopefully you're saying, well, what model? I don't know. Cookies based on days equation would be the original amount I started with, 80, times this 1/2, the amount that I'm taking, half to the number of days. And so when I do this, we can actually just type, right? I don't have a calculator with me, so we'll use OneNote. If I do 80 times 0.5 raised to the, was it 10th power? Boom. So that's not many cookies left. All right, so I guess you're taking little bites out of cookies. And so that's what you get. All right, so let's go back, let's go down here. Keep it going with caffeine, and a lot of metabolic processes in the body or outside of the body in chemistry class kind of work this way, where things are consumed at a half-life kind of rate. And how much caffeine after 5 hours? 5 hours is 1 half-life, right? So that means you'd have half of it. And what does it say? So it's just like up above, similar process. So if I have the hours, amount remaining, why don't you guys hit pause and you go fill out the table. Okay, well, hopefully you hit pause and actually did this instead of sitting there. Remember, no vegetable stuff, no rutabagas in my class. All right, so what does it say? 5, 10, 1, 2. Oh, it's interesting. We started 5 and 10, then go back to 1 and 2, huh? So 5 hours is 1 half-life. Well, that's half of the 80, which is 40. This is half of the half. This is 2 half-lives. So half of the 80, which is 20. And now it's like, well, what am I going to do for 1 hour? How many half-lives is 1 hour? And I have to think about this. And what it ends up being, I don't have room to write this down here. What exponential model? Let's go on to B. What exponential model will do that? I think it says F, call it F, fine. F based on time, T in this case being the number of days, is the initial amount of 80. And I'm still saying I'm taking half to how many times? So what I say is I'm raising half to a number of half-lives. Is it lives or lives? Anyway, I don't know if I should have VES or FSS, but anyway, we'll say half-lives. Now, how many half-lives in 1 hour? Well, it's a fifth of a half-life. So I really need to raise it to the 1/5 power. And what you see is 5 is the length of each half-life. So when I come up here under 1, let me type it, see if it lets me put the cursor right here. Yeah, nice. 80 times 0.5. You could do 1/2, but you have to remember the parentheses then. Raised to the, now I will need parentheses for this, because I want to force it raised to the no wait, there's no parenthesis. Raised to the 1/5 power, and that would be it. And if I just copy and paste this down below, I should be able to do it for 2 hours. You do it too now. Well, actually, hopefully you all already did all of that. And I'll put 2/5 here. I'm going to delete all that, and it recalcs. Nice. And then those should be the other answers for 1 and 2 hours. Hopefully that's a good refresher of the exponential and half-life from last year. Okay. All right, we checked everything. 3 hours after peak level. Well, I think it's still on my cursor. You do it. And we wanted one about 8 hours. And then one about 20 hours, right? I should be able to just type into here and say 3. Again, hit pause. You do this. 52.78. All right, that looks reasonable. What was the next one? 8 hours. Now these are not even numbers of half-lives. Now, of course, 8 hours should be somewhere in between the 5 and the 10 up here, so it should be somewhere between 40 and 20, and indeed it is. And I think this next one was 20 hours, right? 20 hours. Okay, 20 divided by 5. Actually, that's 4 half-lives, so it should be an even number, and it's 5. Cool. So we got that one, and that one, and that one. Okay, hopefully this isn't too bad, and this is a nice, easy way. We'll get into some trickier word problems soon. If you're bold enough, try doing the I don't know what's it called. What's the other worksheet called? The Forensic Mysteries one without help. That's if you're bold. So it looks like this is the same equation here, except we now have the half-life not at 5 hours, but at 8 hours. So half is every 8 hours because this person has a slower metabolism. I mean, you might have, there are probably published articles. I may have looked it up when I looked up these problems, that the half-life for caffeine in the average individual is 5 hours, but people's metabolisms are all over the place, so it's going to vary by individual. So go ahead and work through E and F and G and hit pause. Go. Do it. Run these calculations. Okay, I'm back. Hopefully I actually did it. F of t would be 80 times 1/2 to the t over 8 now. And again, don't forget that I'm raising 1/2 to the number of half-lives, and it can be a fractional or decimal thing. It's very important to remember that is the number of half-lives. Okay, same kind of grid as before. I didn't want pink. I want 1, 5, 10, 20, and this is the time, and this is the f of t. I think you had 73.4 milligrams, 51.9, 33.6, and 14.14. Call it 14.2. Okay. Which half-time results in caffeine? Well, 5 hours. 5, of course. A smaller half-life means it gets consumed faster. Now, this is very important. Don't wait for me to answer it. I'll put it in pink so it stands out more. Use laws of exponents to rewrite the function so the exponent is just t, not t over 5. For easy reference, let's copy down the function from up above. F of t, what was it, 80 times 1/2 to the t over 5 power. Now, go, do it. Hit pause. See if you can think about how you could rewrite this so there's only a t outside the parenthesis. Go. Okay, hopefully you said, well, there's still an 80, and I want some parenthesis, and I want it to be the t power. So let's start with that. What could I put inside of here so that instead of a t over 5, it's just a t? Well, remember power to a power rule? Wouldn't that be the same as saying, I'll do it in purple, 1/2 to the 1/5 power? If I do power to a power on that, won't that get me back to the original? Nice. And so, fine, I'll say 80. And if you take 1/2 and raise it to the 1/5 power, 5th root of 1/2, you should get 0.871. Now, why is that interesting? In layman's terms, you can now say, well, let me put the t back on here. You can now say, well, each hour, at the end of the hour, there's 87.1% of what we started with. So at the end of the hour, I have consumed almost 13% of the caffeine that was in my body. And that's a nice, easy way to say it that common folk might understand more. Okay, do the same thing for I. Go, don't wait for me. See what this percentage is for the 8-hour half-life. Okay, I'm back. Hopefully you said f of t equals 80, 1/2 to the t over 8. And you said, okay, fine, that's 80, 1/2 to the 1/8 power. And then that's 80 times 0.917 to the t power. So when your half-life is 8 hours, at the end of each hour you have 91.7% of what you started the hour with. Okay. So who knew that exponent properties would come up with such a nice, useful conversion? And now if I graph these two graphs, it's just like pulling the numbers up from above. What hours did we use? I think we had a 20-hour mark. Let's see, I'll make my scale 10, 20 hours, 30 hours, 40. I'll extend the graph out a little bit beyond what I had from above. So this will be the hours that go by. And we'll have the milligrams of caffeine. And if you think about it, we need to go up to like 80, right? So I don't know, make that 20, 40. Oh, I'm gonna go off my grid. 60, and we all started at 80. Okay, make your graph. You got two tables of values. The first one I'll do in purple. The 5-hour one I'll do in purple. So we'll say the no, that's blue. Purple graph will be the 5-hour half-life. And then I'll do in green. It looked like I had a table in green. The 8-hour half-life. Okay, graph them. Let's see, the 5-hour half-life. I can't remember. At 5. Okay, well that's easy just to come up with the numbers. So at 5, started at 80. 5 hours, I'm at 40. So that's right there. At 10 hours, I'm at 20. I think that's what I had, right? Should have. At 10 hours, I was at 20, right? And I'll just make up the other numbers because at 15 hours, I'm at 10. At 20 hours, I'm at 5. And it goes down from there, and it's going to look pretty asymptotic. Okay. Easy enough. So that is, well, easy to see where those are. So for the 8-hour half-life, it's actually probably easiest just to do the same thing. Let's do the same points. 40 would now come at 8, right? Forget the numbers we did up above. Be like right here. At 20 would come not at 10, but at 16. So that's like right here. 10 would come at half of, not at 15, but with 24. This can be like right here. And then half of 10, 32. So that's like right here. That's good enough. Okay. So are they different? Yeah, sure. One's faster, right? Call it the 8 hours fat. I did 8 hour instead of the 5 hour. 8 hours slower. Getting there. Do they intersect? Only at the start point. Only at 080. Okay. Now, theoretically, did carbon dating last year also? How many more problems do we have? It's getting. How long is my videos? Oh no. Am I recording? Hopefully I'm recording. I'm at 15 minutes. I guess I can finish in one video. I don't like to make the recordings too long. Okay, so there'll only be 50% left. Well, half-life means 5,730 years. And hopefully you can see that carbon-14 dating is very common with biological materials, but it only works for a certain number of years. You can't use carbon-14 dating for something that's a million years old. There's other radiocarbon dating for that. Okay, so T years after the death of the person to which it belonged. F of T is equal to 1/2 to the number of half-lives, so it's T over 5730. Okay, let's use it. Percent of carbon-14 2,000 years after a death. Well, I don't know. Let's just look at this. How many years do I want to go out to? At least 4 or 5 half-lives. So where should I start? I think I'll start at 5730. Be 1 half-life. Call that the number of half-lives. And then if I have 2, yeah, I won't be able to fit my 2 down there. Let's actually graph the number of half-lives down here. If I put 2 half-lives here, or 3 half-lives here, and 4 half-lives, that'd be, what, 11,460? That'd be 17,190. And then 4 times, that's 20,000 plus 2,800, so 22,970, is it? 920? I don't know, something like that, close enough. What's the percent remaining? Okay, let's see, percent remaining. I started at 100. How many dots? That's the middle, right? That's 50%. Half of that, oh no, I had 7. That's a weird scale, but 25%. Half of that would be 12.5%. I want 2,000, and let's get this graph now. So this is here. 1 half-life is 50%. Let's do it in a different color. Purple. No, blue. Blue. 2 half-lives is 25%. 3 half-lives is 12.5%. And then 4 is something like down there. Okay, good enough for our purposes. Now, if I had 2,000 years, ooh, it's less than half of that. It's like a third, so it'd be like right here, and then it'd go over. Now, what is that about? Looks like it's approximately equal to 75%. Okay, algebraically, well, let's think about that. I want 1/2 to the 2,000 over 5730 to be equal to what? And I think if you type that in, then you're going to get 0.7851. Now, of course, that's more accurate, but the graph wasn't too bad. As quickly as I made this scale, 75%, 78%, not bad, actually. So the power of graphing and approximation. And this is a great technique when computers do all the hard work for us anyway. Okay. A fragment contains 64% of the carbon-14 that is normally found. How long ago did the person die? Okay, well I can figure that out. I know this side. I know the left side is 0.64. It looks like I don't know what was the equivalent of the 2000 up here. So let me rewrite the above equation. 1/2 to the t over 5730 equals 0.64. Now, a couple ways to solve this. I can map that into logs, or I can remember that I can take the log of both sides. Let's do that. And this is my solving technique we did all last week. If I take the log of both sides, remember a log is a power. A log of this will bring that power. Then remember the power is the fraction of t over 5730. That whole fraction comes down to the main line. Where can I rewrite? Actually, I can get myself some more space here. There, a lot more space. So when I do that, I have t over 5730 times the log, I'm just write it as 0.5, equal to the log of 0.64. So t is equal to log of 0.64 divided by the log of 0.5, and I'll multiply that by 5730. No, not 53. Okay, hopefully you're following along. Do it. You type it in, hit pause. Don't just wait. And if you type all that in, I think you get 3,689.3 years, and that is exactly how a scientist would be saying, you know, this mastodon got buried this long ago in ice and things like that. So, okay. Well, this is 3 is a good problem to try, and it's a relatively easy one. Try it out and see if you can do it according to what we did up here. I'm not going to bother because we just did a bunch of these. And then you can just try your homework, and we'll skip that one for now. Well, how about this one? This one's good. It's got a good name for it anyway. Try to set that problem up. Hit pause. Go. Half-life is 134. So what would the setup be, and what's the answer? Hit pause. Go. Okay. Hopefully you said, well, I got 1 kilogram. I started with 12 kilograms. And what happened was I took my half to the number of half-lives power. The number of half-lives would be t over 134. Because if it was 134 years old exactly, that'd be 1 half-life, so it'd be 6 kilograms. So obviously it's more than 134 years. If we had to approximate, you know, you're taking half of 12 is 6, half of 6 is 3, half of 3 is 1.5, right? So it's a little bit more than 4 half-lives, so worth looking in the ballpark of 800 years or so, just by approximating. And that's a good way to make sure you're not making silly calculation mistakes, is just think about it for a sec. And actually, I don't know if it's that many years. Did I do that wrong? I think half of 12 is 6, half of 6 is 3. It's actually 3 and something half-lives, so more like 400 years. I knew I made some kind of silly mistake when I was talking. Okay, we'll solve it. Now, before I take the half, the log of both sides, remember, I should get solve for the exponential and get it all by itself. So I really should get 1 over 12 is equal to 1/2 to the t over 134 power. Now when I log both sides, log that, log the right, I end up having, well, you can see that this is going to come down to the main line. So you'll have t over 134 is equal to the log of 1/12 divided by the log of 1/2. And then you should get t is equal to 480.4 years. Okay, hopefully that's good enough to get you through your homework. Have a good weekend, everybody. Bye.